Hi there. The purpose of this circuit is to explain a parallel resonant circuit. What do we mean by resonance? What we mean by resonance is at this point here we're going to get an output voltage across this parallel network here, and that output voltage will reach a peak at a particular frequency, which we call the resonant frequency, and frequencies below that value, frequencies above that value, the voltage will go down and we'll get a peak at a particular value. If we plug our values 2.7 nanofarads, 1 millihenry into this equation, do the calculation, it comes out to be 97,000 hertz, 97 kilohertz. We would expect the reactance of that capacitor to offset exactly the reactance of the inductor, which is approximately 600 ohms at 97 kilohertz, and what we're left with is just a resistive voltage divider, where if you do the calculation for a voltage divider, the voltage coming out here will be 4.6 volts, and because the reactance of the capacitor and inductor cancel out, this particular voltage should be completely in phase with the input voltage. Got a sine wave going in, 10 volts peak, and at a resonant frequency we would expect 4.6 volts coming out peak, and we expect the voltage to be completely in phase with the input. Why would it be in phase? Resistors convert energy, they don't store. Capacitors store it in the electric field, inductors store energy in the magnetic field. At a particular resonant frequency, the reactance of capacitor equals the reactance of the coil, the inductor, and they cancel each other out, and we get a voltage divider, we get a peak value coming out, 4.6 volts. Above and below that particular frequency, the voltage will go down, and we can prove that now. So on the screen we've got, if we wind it down, we've got there, for example, wind it down, we've got 50,000 hertz going in, lower frequency than the predicted resonance of 97 kilohertz, and we can see the purple one, the smaller one there, is what's coming out. It's quite a small voltage. You can see it measures there is 300 millivolts peak to peak, 150 volts peak. If we increase the frequency from the function generator, we can see that the voltage coming out is increasing, and it's also the phase shift starting to go in phase with the sine wave going in. We're now at 90 kilohertz. The voltage is increasing. You can see it peaking, it's peaking, and there at that point there, the voltage coming out is peaked and it's in phase, completely in sync with the sine wave going in. If we increase the frequency further, then the output voltage goes out of phase and it starts decreasing again. So if we go down to resonance, where the sine waves in and out, or out and in, completely in phase, we can measure it, turn the time base down a little bit to get it as accurate as possible, tweak the frequency going in where they cross the zero axis, and what we can see there, yep, that's good. We can see reading off here 97.7 kilohertz, which matches the theory that we previously predicted. So lower frequencies, the voltage coming out at lower frequencies, the voltage is leading the input, gets to a peak before V in, so the voltage leads. If we go particular resonant frequency, we're completely in phase at 97 kilohertz. We increase the frequency further, V out reduces, and now V out lags the sine wave going in, which is what we would expect. So what we've got here is a resonant circuit. We've proved the voltage gets to a peak. So what is happening here, if we look at current in the parallel network, the current reaches a minimum at 100 kilohertz, and then afterwards at lower frequencies the inductor tends towards a short circuit and the capacitor tends towards an open circuit, so the current increases. At higher frequencies above resonance, the capacitor tends towards a short circuit and the inductor tends towards an open circuit, but the short circuit of the capacitor increases the current. So we get a peak in the circuit impedance at resonance where it just equals the resistive voltage divider, and we get minimum current out of it. So at peak input impedance or impedance of the circuit, we get maximum voltage coming out at this point across the parallel network. So why have we got a voltage divider here? This resistor is put in there to create a voltage divider so that we can actually see a separate output voltage, separated, discriminated from the input voltage here, and we can see on the screen that the voltage reaches a peak at a particular frequency of 97 kilohertz, or round it off to be 100 kilohertz, and we've proved that by experiment. This circuit is also a bandpass filter, so at the moment we've got a sine wave going in. We'll just adjust the time base to see more. We've got a sine wave going in. If we go back to resonance, and we change the input voltage to a square wave, we still get a sine wave coming out. So why would you have a square wave going in but just a sine wave coming out? A square wave from the function generator is made up of adding sine waves together of different amplitudes and different frequencies. For a square wave, we add odd harmonics. So we've got a base frequency, we've got another harmonic frequency, 3 times the base, 5 times the base, 7 times the base, and so on. Higher frequencies make that up. What this circuit does is, because it's a bandpass filter, it will only pass the signal through or a narrow band centered around 97 kilohertz. So if we go to resonance, although we have a square wave going in, it filters out all the higher frequency components of that square wave, and we only get a sine wave coming out at resonance. If we go below resonance, again the output goes down and it's a bit distorted. Above resonance, again the output voltage comes down and it tends to more at higher frequencies to a triangle wave. But at resonance you do get out just the base frequency there, the base sine wave frequency. So it proves that it's a band pass filter. Thank you for watching. I do have a spreadsheet with all the breakdown of the voltages and currents in the circuit. Please put any comments below, and thank you for watching.